Okay, so last time we talked about the coupling constant. Okay, so yeah, just here if you have kind of split peaks, okay, so the distance between the peaks, okay, that's what we call the J values. Okay, so if you have the two proton coupled to each other, okay, the J value should be same. Okay, so the JAB equal to JBC, and so this J value is independent of your strength of the NMR instrument. Okay. And so yeah, because if you two neighboring hydrogen case, so neighboring hydrogen case, so have same kind of J coupling constant, okay, then we can apply n+1 rule, okay. So what's that mean, okay? Give you one example, okay. Right. So for example, okay, so for the middle hydrogen case, there are two neighboring hydrogen case, so okay. So we can call them kind of this one HA, okay. This is HB, this is HC, okay. All right. So now we look at kind of the HA signal, okay. So if there's so if the coupling between HB to HA same to the coupling between HC to HA, okay. So that's we can label as kind of H B A equals to kind of JCAK. Okay, JBA equal to JCAK. Coupling constant are different, same case. So if they're same case, and then you can apply n plus rule. Okay, so what's that happen? Kind of okay. So if there's no no coupling happened. Okay, so the HA should only show one signal. Okay, just singlet. Okay, but it has kind of the two hydrogen kind of in three bond way, okay, two neighboring hydrogen, and then will happen, okay, then will couple, okay. So we do the HB first, okay. So because the HB only one protons, okay, and then we apply n+1 rule, okay, and then that's you HA split kind of two signal, okay. Okay. And this distance, okay, we call kind of the JBA, okay. So that's HB coupling, okay. All right, and then these two things quick continue couple with the HC, okay, and then split again, okay. So because HA only one protons, okay, and then each become kind of the two again, okay. All right. Right, because the HBC BA equals kind of HC, okay. So that's the one of the signal actually kind of overlapped, okay. And eventually, generate something like this, okay. So that's the HCA, okay. And then JC, okay. So that's HC coupling, okay. Right. Because the HBA, JBA equals kind of JCA, okay, the coupling constant, okay. So same, okay. So then we can apply n+1 rule, okay. So A has two neighboring hydrogen, okay. So n+1, okay. So that's 2 + 1, okay. So you get 3 peaks, okay. So that's why eventually, okay. So you A get kind of triplet, okay. Triplet, okay. So the middle signal kind of the reinforced, okay. You have kind of the overlapped, okay. So that's why intensity of these 3 peaks kind of 2 to 1 to 1, okay. All right, okay. All right, so that's the J coupling constant kind of same, okay. But if the J coupling constant are different, okay, so the situation gets more complicated, okay. So you cannot apply n+1 rule, okay. Here's one example, okay, similar to the HA, HB, HC, okay. So here we look at the HM, okay. So middle hydrogen, okay. So this middle hydrogen has two neighboring hydrogen, okay, HA and also HX, okay. But in this case, okay, so the coupling between HA to HM are different from HX to HM, okay. So this case is the JAM bigger than the JMX, okay. So right. Okay, so in this case we can analyze it again, okay. Right, so if there's no coupling, HM, okay, should show only one singlet, one signal, okay. and then it will first couple with the HA, okay, so here, okay, and HA has kind of a very huge influence here to the HM, okay, so bigger, the coupling constant, okay, so that's here, big, okay, and then split here the HM signal into two, okay, and then the HM, okay, further couple with the HX, okay, HS has the very relative kind of a smaller constant, coupling constant here, which HM, okay, and then that's the coupling constant HMX, okay, and then you further split kind of into another two doublet, doublet, okay. So eventually, okay, so generate kind of doublet or doublet, okay. So that's here the this case kind of if the coupling constant are different, okay, you cannot apply the n+1 rule, okay. So although HM has two neighboring hydrogen, okay, but it's got kind of 4 peaks, okay. So those situation, please keep in mind, okay. So we'll see kind of maybe in future kind of quiz or exam, okay. Right. And here's the real example, okay. So this is the bromo ethene, okay, bromo ethene, okay. So 3 proton HA, HB, HC, okay. So these 3 protons all are in 3 bond distance, okay. So that means kind of they can all couple to each other, okay. And then they have different coupling constants, okay. HAB are different from BC, also different from HAC, okay. All right, okay. So we just look at one of the signal, okay. Let's see, HB, okay. So look at the B, okay. B coupled with HA and also HC, okay. And then they have different coupling constants, okay. So C, okay, HC coupling constant is kind of the 7.1, okay. So that's give kind of 2 peaks, okay. And then the coupling constant from the A, okay, HA is the 1.8, okay. So that's the different coupling constant, and then you eventually for B signal, okay, split into kind of doublet or doublet, okay. So that's please keep in mind, okay. And so similar situation actually for the HA signal and also the HC signal, okay. So actually all 3 protons, okay, become kind of W or doublet, okay. So that's the can see kind of 4 peaks, okay. Right. Okay, so forgot the so if you have any question, okay, so please type in the chat window, okay. Right. Okay, so now a little bit easy topic now here. How do you prepare the NMR sample, okay? So when we run NMR experiment, okay, so we need to dissolve sample into the solution, okay, so solvent, okay, and make a solution, homogeneous solution, okay, and no matter it's the solid sample or liquid sample, okay. And but if we use regular solvent, okay, so like the methane chloride, okay, chloroform, okay, so the solvent itself, okay, also we have some kind of the protons, okay. So if we directly record, okay, the solvent proton, okay, solvent hydrogen, okay, will be huge, okay, overlapped with the signal of the samples, okay. So in this case, we have to use some special solvent, okay, called deuterium solvent, okay. So in this solvent, okay, so all the hydrogen will be replaced by deuterium, okay. The deuterium is kind of H2, okay. So that's one of the hydrogen kind of the isotope, okay. So the hydrogen kind of several isotope, okay. So H1 and that we call proton and H2 deuterium, okay. And so although H2, okay, so deuterium also NMR active, okay, but it will show at different region, okay, different from kind of the proton H1, okay. So remember in the previous class, okay, I showed kind of the for proton the NMR calculation, we can do this way, okay. Gamma and 2 pi beta xt, okay. And this gamma is related to the individual atom different kind of nucleus, okay. So the H2 gamma are different from kind of H1 gamma, okay, deuterium different kind of protons, okay. And then the deuterium will show kind of the different kind of the frequency, okay, and then it shows kind of different area in the whole NMR range, okay. So in other words, okay, so you won't see kind of deuterium signal in the regular proton NMR, okay. Okay, so the following are some kind of common organic NMR solvent, okay. And the first one is the CD03, okay, that's the deuterium chloroform, okay. So replace the one hydrogen in the chloroform with the deuterium, okay. And the second one kind of deuterium water, okay. So replace both hydrogen in the water, okay. So with the deuterium, okay. And the last one is kind of deuterium DMSO, okay. So this one, okay, so yeah, DMSO supposed to be a 2 yeah, methyl group, okay, and then you replace the all 6 hydrogen with the deuterium, okay, so that's why I call it D6 DMSO, okay. So yeah, those solvent we use a lot in the organic kind of the class, okay, especially kind of the NMR instrument, okay. So yeah, probably in 2 weeks, okay, so we'll learn how to record the proton NMR, okay, and then we will use the CD03, okay. Just the one thing, please keep in mind, okay, so actually the people intend don't replace all the deuterium kind of in the CD03 with replace all the protons with the CD03 in the solvent. Okay, so yeah, actually kind of there's a little bit the proton left. Okay, so yeah, quite often when you purchase the CD03, okay, label like 99.8% kind of CD03. Okay, actually there's about the 0.2% kind of proton. Okay, not replaced by deuterium. Okay. Right. Okay. So those proton will show up in the proton NMR. Okay. So yeah, when you record proton NMR, quite often you see some kind of like this. Okay. So that's 0 ppm. Okay. So here maybe like 10 ppm. Okay. Right. And then there's some kind of peak. Okay. So yeah, small peak about 7.28 ppm. Okay. So this peak actually not from the U sample, okay. So this peak actually from CDCl3, okay. So yeah, write it down, okay. So yeah, 7.28. Sometimes people said kind of 7.24, okay. So yeah, pretty much. That's from CDCl3, okay. So okay. A reason why the people intend to leave a little bit the protons, okay. So yeah, so that's help to kind of the we call fix the field, okay. So yeah, tell instrument kind of this is proton NMR and that's the standard, okay. So yeah, somehow kind of like internal standard, okay. So that's here like this, okay. Yeah, please remember these signals, okay. Okay, and here's kind of some the picture of the real NMR samples, okay. And so yeah, you dissolve your sample in deuterium solvent, okay, and then transfer into this we call the NMR tubes, okay. And then we insert this tube into an NMR instrument, okay, and then we can record NMR, okay. Okay, so yeah, those we will learn how to do it kind of probably in 2 weeks later, okay. So yeah. All right, okay. Here's kind of show you how to solve some kind of NMR spectrum kind of and so proton NMR especially, okay. So yeah, those questions we will see kind of quite often in the probably quiz 5 and those exam 3, okay. So that's kind of I would say kind of not easy question, but if you follow some rule, okay, should be able to kind of answer it, okay. Right. So for this kind of question, okay, so normally I gave you formula, okay, and I gave you kind of proton NMR. Ask you kind of figure out what structures, okay. So for this kind of question, okay, so you do it stepwise, okay. The first step, okay, so yeah. Okay, calculate DU number, okay. Okay. All right. This one actually you guys can do it, okay. So can anyone tell me what's the DU number for C9H12? Okay. So yeah. Okay, that's pretty fast. Okay, 4. That's right. Okay, so that's 4. Okay. Right. Okay. So remember. Okay. So yeah. In the class I said kind of if the DU number is the 4 or more than 4. Okay. More likely there's a benzene ring in this molecule. Okay. So benzene. Okay. Because benzene has one ring structure, 3 double bond. Okay. So that's give you a 4 degree of saturation. Normally, no other kind of functional group, okay, can give so high degree of saturation. Okay. And then once you figure out their kind of the benzene, okay, the first thing you need to do is kind of look at the how many protons, okay. So yeah, numbers protons, okay, at the 7 ppm, okay, about 7 ppm, okay, at about 7 ppm, okay. Right. So yeah, then that's the information can tell kind of the substitution the pattern on the actually no substitution pattern, how many substitution, okay, on the benzene, okay. Right. So yeah, so we know that kind of benzene has 6 protons, okay, 6 protons on it, okay. And so yeah, if we showed as kind of 5 proton here like this, okay, so that means kind of monosubstitute benzene, okay, because one of the proton, okay, will be replaced by substitute, okay, so that's something, okay, and other 5 still keep there, okay. And same thing, okay. So yeah, if you see kind of 4 proton around the other, yeah, 7, okay. So that means kind of disubstitute the other, yeah, bending, okay. If 3 proton around 7, that means trisubstitute bending, okay. So that's kind of important, okay. All right. Okay, so that's the first step, okay. And then second step, okay. You need to generate kind of the fragments, okay. And this step, okay, so you have to make sure all the atoms are countable. So yeah, you have kind of yeah, same number of your carbon, hydrogen, or whatever atom, okay, showed in kind of your formula, okay. Okay, and then for this example, okay, so we are clearly see kind of we have the first fragment monosubstitute bending, okay. And second kind of there's one yeah, hydrogen here, okay, so yeah, multiplate, okay, so yeah, that we can see kind of the property is yeah, CH, okay. And then there's no oxygen, no nitrogen, okay, so that has to be kind of CH, okay. All right, and then there's kind of 6 protons, okay, so yeah, 6 protons, okay, more likely should be kind of 2 CH3, okay, so yeah. Yeah, cannot be kind of only 1 carbon with 6 hydrogen, okay, that's break up octet, okay. 2 yeah, CH3, okay. All right, so and then combine with monosubstitute bending, okay, so now yeah, we have kind of 3 fragments, okay. Once you have these 3 fragments, okay, repeat bending, okay, bending, okay, so calculate the DO number, okay, so yeah, that's more than 4, okay, equals 4, okay, so if we 4 or more than 4, okay, so that means yeah, there's yeah, bending in the molecule, okay, and then look at kind of yeah, how many proton, okay, at about yeah, 7, okay, about 7, okay, because yeah, proton in bending, okay, show the absorption, show kind of NMR signal at 7, okay, 7, okay, right, and then if 5 protons monosubstitute bending, okay, 4 protons, okay, disubstitute bending, okay, 3 protons, okay, trisubstitute bending, okay, so yeah, that's yeah. All right, okay. So now we have yeah, these 3 fragments, okay, so yeah, you need to look at back kind of formula, okay, calculate kind of carbon number, hydrogen number, okay, to see any missing atom, okay. Right, so 1 carbon, 2 carbon, 3 carbon, 3 carbon plus yeah, the 6 carbon on the yeah, bending. We should have kind of totally 9 carbons, okay, all the carbon accountable, okay, and then hydrogen, okay, 1 here, 3 here, that's 4 plus yeah, the yeah, kind of yeah, 6 carbon, okay, so 6 carbon. 1 plus yeah, 6, that should be kind of yeah, the 7 plus 5 carbon on bending, 12 carbon, 12 hydrogen, okay. Okay, so all the hydrogen accountable, okay, 1 and then 6, okay, and then 5, okay, so 12 hydrogen, okay. Right, so that means yeah, we don't miss any atoms, okay. Right, so now yeah, we move to the third step, okay. So try to combine the yeah, merge, okay, merge the fragment, okay. So that here we generate kind of the big piece, eventually get kind of full structure, okay. So this step kind of important. You have to apply kind of the spin coupling, okay. So N+1 rule, okay. So that's how to kind of combine them together, okay. All right. So yeah. Okay, so the most okay. All right, okay. So we look at kind of split pattern for individual peaks, okay. So bending normally don't need to look at it, okay. All right. So for the CH, okay, you see kind of pretty much the should be 7 peaks, okay. There's kind of 2 small peaks here and here, okay. And then for this here, the 2CH2, okay, looks like kind of the doublet, okay, so 2 peaks, okay. Right, okay, so yeah, we have 1 H, yeah, we call kind of the septet, okay, and then 6 protons kind of the doublet, okay. So that's actually we learning this part in the class here, maybe on Monday, okay. So this should be kind of the isopropyl group, okay, isopropyl group, okay. Yeah, because this the middle hydrogen, okay, has the totally 6 neighboring hydrogen, okay. So this 2 methyl group, okay. So as kind of this neighboring hydrogen, okay, so we have 3 bond away, okay, 6, that's give kind of the N+1 rule, okay, so yeah, the 7 yeah, peaks, okay, so that's here the heptat, okay, septet, okay. Right, and then yeah, for this 2 methyl group, okay, only 1 hydrogen, okay, so yeah, in 3 bond away, okay, so that's we apply N+1 rule, 1+1, 2, okay, so that's why it's doublet, okay. Right, so that's here the yeah, we kind of here the merge these 2 fragments together, okay. So now only 2 fragments, okay. So that's pretty easy, okay. So one's monosubstitute bending, one's kind of the isopropyl group, okay. So that's should be isopropyl bending, Okay, all right. So that's how do you do this kind of question. Okay, all right. And then next kind of we practice on question okay from the discussion yesterday. Okay, this one. Okay. Yeah, can see the full whole thing. Okay. All right. Okay. Again, we do the similar thing. Okay. So so this time okay, so different from the previous example. Okay. This one okay, so also provide you the IR. Okay. So that's very useful. Okay. So IR actually kind of can give you kind of information about functional group. Okay. Right. Okay. So we start from still the DU number calculation. Okay. So this formula is kind of C6H12O2. Okay. Right, C6H12O2. Okay, so can anyone tell me what's the DU number for this one? Okay, C6H12O2. What's the degree of saturation for this molecule? Yeah, please type the answer in the chat window. Okay. Yeah, that's right. Okay, 1. Okay, right, good. Okay. So that's 1 degree of saturation. Okay, so that's that means there's no bonding in this molecule. Okay, probably 1 ring or maybe the 1 double bond. Okay, right. So next step. Okay, next step. Okay, so that's we get 1 extra step. Okay, so that's different from the previous example. Next step we try to generate kind of fragment. Okay, so next step. Okay, for if IR provided for you. Okay, next step okay, you need to look at the IR. Okay, so that's step 1, step 2. Okay, and try to figure out what kind of function group. Okay. So if IR provided for you, okay, so like I said, okay, so the first thing you look at is any peak around like here the 1700, okay, so that tell you whether kind of carbonyl group in this molecule, okay. All right, for this example, okay, so this question, okay, definitely we see kind of huge peak around kind of 1700, okay. So that means here there's a carbonyl group in this molecule, okay. So that's also kind of where's 1 degree of saturation come from, okay. So that's coming from carbonyl, okay. But we learn a lot of carbonyl group, okay. So a lot of compound has the carbonyl group, okay. Aldehyde, ketone, okay. So amide, okay, or kind of ester acid, okay, hydride or some kind of acid chloride, okay. What kind of the carboxylic acid group, okay, or what kind of carbonyl group in this case? So you have to look at other kind of signals, okay. And you notice, okay, so there kind of huge peak, okay. So from probably 2500 to 3600, okay. So that's typical kind of carboxylic peak, okay. So that means this is kind of should be carboxylic, okay. Right, carboxylic, okay. And also you can get some information from the formula, okay. Formula has 2 oxygen, okay. So carboxylic has 2 oxygen, okay. That's consistent with kind of formula, okay. Right. So that's the IR done, okay. Now we move kind of try to generate kind of fragment, okay. So this one we have to use kind of the proton NMR, okay. So for proton NMR, so we have 3 peaks, okay. So 1 to 2 to 9, okay. So because they are totally 12 protons, okay, it is identified as 1 proton, okay, and then 2 proton, 9 proton, okay. So 1 proton very high, 12 ppm, okay. So if you look at kind of the IR table, when you kind of do it, okay, make sure you bring your IR table, not IR table, okay, NMR table, okay. So proton, okay. So that's the definitely from carboxylic, okay. So because the carboxylic kind of proton, about 9, okay. So that's COH, right. And then this is kind of the 2 proton, okay. 2 proton, so we can see kind of CH2, okay. Right. This is 9 proton, okay. So a tricky thing for these 2 guys, okay. So that's only singlet, okay. Singlet means they are the no neighboring hydrogen, okay. No neighboring hydrogen, okay. So can anyone come up with some structure, okay? So draw the know what's the structure for this one, okay? Anyone did it? If you like, you can turn the annotation, okay? Right. So both are singlet, okay, but the totally the no neighboring hydrogen, okay? So 9 protons, okay. So we can think about kind of 3 CH3. Right, 3 CH3. Okay. Right, so that's a really tricky one, okay. All right, here's kind of another important kind of the NMR pattern, okay. So proton pattern for you guys, okay. So if you see kind of 9 proton singlet, okay, 9 proton singlet, okay. So that will be kind of the T-butyl group, okay. 9 proton singlet, okay? Because only T-butyl group can give kind of all 9 proton, no neighboring hydrogen, okay? So no hydrogen kind of in 3 bond away, okay? Only T-butyl group, okay? So that's your thing, okay? All right, okay, next kind of we have CH2 here, okay, so T-butyl group, okay, and then Kafkasid, okay, so only 3 fragment, okay, we look at kind of how many protons, okay, so how many hydrogen, okay, so 1 from here, okay, 2 from here, okay, and then 9 from here, okay, totally 9, totally kind of 12 protons, okay, that's right, okay, and carbon, okay, so 4, 5, 6 carbon, okay, 2 oxygen, okay, so all atoms are countable, okay, so next kind of piece them together, okay, so this H2 has kind of 2 opening, okay, so this carboxylic acid and also T-butyl group case only has kind of 1 opening. That's definitely kind of put the CH2 in the middle, okay, and then 1 end connect with the T-butyl group, okay. Another end, okay, connect with the carboxylic acid, okay. All right, so that's your final structure, okay. Once you're done, okay, so make sure go back to check it, okay. So we know that kind of for this one should be kind of singlet, okay, so CH2 singlet, okay, and then T-butyl group singlet, okay, so you look at that, you make sure you double check, okay. You find kind of indeed, okay, so for all these 2 protons, okay, there are no neighboring hydrogen in 3 bond away, okay, so that should be singlet, okay. So that's the right answer for this one, okay. All right, okay, and then the last question, okay, from the discussion, worksheet yesterday, okay, so actually kind of I moved to okay, so I generate some of the kind of slide here, okay, so use that one to explain kind of how do you answer this kind of question, okay. Right. Okay, so there's another type of question, okay, so different from previous. The previous one I give kind of formula and also the NMR spectrum, ask you to figure out structure, okay. So this one, okay, I give you structure, okay, ask kind of try to draw it to the NMR proton kind of okay, proton NMRs, okay. So for this kind of question, okay, so how do we resolve it, okay, so right, the first thing you need to do is kind of figure out how many signals you should see for this molecule, okay. How many kind of proton signal, okay. Right, so we have this aldehyde, okay. Can anyone tell me kind of how many different proton signal, okay? Pull that back. Okay, so let's do this way, okay. Right, okay. So we just do this way, okay, temporary, okay. All right, how many signal, okay? So 3, 4, okay, 4 is the right answer, okay, because okay. So this is the 1, okay, A, okay, and then there's no proton here, okay, but there's 1 proton here, okay, so that should be B, okay, I just label B here, okay. And these 2 will be same, we call C, okay, so related back on the rotation axis, the symmetry plane, okay. These 2 methods will be same kind of D, okay. All right, okay, so that's done. Okay, so that's here we have totally the 4 different protons, okay. Right, and then for your beginner, okay, so my suggestion kind of develop some kind of small table, okay, and then label is here the chemical shaped integration and those here the split pattern, okay. All right, so we labeled here, okay, A, B, C, D, okay, so that's here the 4 signals, okay, and then the first row will list their kind of chemical shaped, okay, so chemical shape kind of delta, okay, so ppm, okay. Right, so that you need to use the NMR kind of the chart, okay, so the table, okay, so make sure bring your NMR chart kind of for the exam quiz, okay, all right. So A is the aldehyde proton, okay, look at kind of your NMR chart, okay, so right, so here, aldehyde, okay, so that's the about 9 to 10, okay, so probably we just kind of call it kind of 9.5 ppm, okay. Right, B is kind of the carbon next to the carbonyl, okay, so B, okay, so look at here, okay, so that's here we call it the carbonyl compound, okay, so right. So hydrogen attached carbon, carbon attached kind of this carbonyl group. Okay, so that's carbonyl protons. Okay, 2.7, 2.7. Okay, so that's maybe we can call kind of 2.4. Okay, right. CAD is just no functional group of byte. Okay, it's just kind of regular the CH2, CH3. Okay, so that also we can find its chemical shape on the NMR table. Okay, right. CH2. Okay, so 1.3. C3. Okay, so 0.9. Okay, so that means kind of the C should be 1.3. Okay, and then D should be kind of 0.9. Right. Okay, so that's you down the chemical shape. Okay, right. So next kind of integration. Okay, so what's kind of the relative height of each peak. Okay, so integration pretty easy. Okay, just how many protons. Okay, so for A just 1. Okay, so B also 1. Okay. C totally 4 protons. Okay, 4 protons. Okay, so 2 pairs of the CH2. Okay, and then D should be 6 protons. Okay, because the 2C3, 2C3. Okay, so 6. Okay, so that's integration. Okay, in the end, okay, it's a split pattern. Okay, so split. Okay, so that's you need to use n+1 rule. Okay, right. Okay, so for A. Okay, so there's only 1 neighboring hydrogen. Okay, so the B. Okay, so 3 bound away. Okay, so and then n+1 rule. Okay, so that should get kind of double. Okay, use D as a label. Okay, right. And then for B. Okay, so get quite complicated. Okay, because the B has kind of the let's say. Okay, so 2 neighboring hydrogen. Okay, so 2 neighboring hydrogen. Okay, and then 1 neighboring hydrogen. Okay, so totally the 5 the protons. Okay, as its neighboring hydrogen. Okay, so 4 from C. Okay, and then 1 from A. Okay, so 5, 6. Okay, looks like sextet. Okay, but maybe they have different kind of coupling constant. Okay, so in this case, we can label as kind of multiplet. Okay, multiplet kind of if you have kind of 4 more than 4. Okay, so 5, 6, 7. Okay, so we can use the label as kind of multiplet. Right, and then for C. Okay, C has kind of the 3 neighboring hydrogen. Okay, so from D, and 1 neighboring hydrogen from kind of the B. Okay, so totally 4 neighboring hydrogen. Okay, 4 neighboring hydrogen. Okay, and then n+1, 5 peaks. Okay, so for C, you can label as multiplet or use that kind of quintet. Okay, quintet. Okay, right, and then for D. Okay, so D only has 2 neighboring hydrogen. Okay, so from C. Okay, so 2 neighboring hydrogen. Okay, and then 2+1, n+2. Okay, n+1. Okay, so that's the triplet. Okay, so 3 peaks. Right, okay, right. So once you done this chart. Okay, so what's M? Oh, M is a multiplet. Okay, right, multiplet. Okay, so normally see the 5 or above 5. Okay, so you can call kind of multiplet. Okay, multiplet. Okay, right. Okay, so once you have this chart. Okay, so that's relatively easy to kind of draw the NMR spectrum. Okay, so you just kind of find on the NMR scale. Okay, so what's the peak? Okay, so for example, A is kind of about the 9.5. Okay, so that's probably about here. Okay, and then let's the doublet, you draw 2 peaks here. Okay, and then for B. Okay, 2.4. Okay, so find 2.4. Okay, here. Okay, and then multiply. Okay, you just gonna draw a bunch of the small peak here. Okay, and then C is kind of the quintet. Okay, so that's about 1.3. Okay, 1.3. Okay, probably this area. Okay, and then just kind of draw 5 peaks. Okay, and D is the doublet. Okay, so the triplet. Okay, so about 0.9. Okay, so that's here. Okay, draw 3 peaks. Okay, and make sure that the peak kind of height. Okay, so relative kind of consistent with their integration ratio. Okay, so for example, A and B you should draw small peaks. Okay, because that's kind of only 1 proton. Okay, and C and D. Okay, so draw into with a huge peak. Okay, because they're kind of 4 protons, 6 protons. Okay, right. Overall, you should generate kind of something like this. Okay, so that's you can do this question kind of like this. Okay, generate kind of chart first. Okay. And in future, okay, so when you are very good at kind of proton NMR, actually kind of you can skip this step. Okay, directly kind of as well you figure out how many the proton signal. Directly kind of draw the peaks on the kind of the NMR scales. Okay, so but you have to pretty good at kind of the chemical shape and also the split pattern and also integrations. Okay, so for your beginnings. Okay, so beginners. Okay, so might kind of do this kind of small chart. Okay, so that's much easier. Okay. All right, okay, so that's we done the chapter, no chapter. Okay, so we done the first part of the chapter 14. Okay, so any questions? So if there's no more questions, okay, so we move to the second part of the NMR chapter, okay, that's the carbon NMR, okay. Right. So NMR not only can record you kind of give you okay, get a new page. Not only kind of record proton signals, okay, and also can report kind of carbon signals, okay. So tell how many different kind of carbon in one molecule, okay. So, but the carbon NMR is different from proton NMR. Proton NMR kind of you record just kind of the most abundant kind of isotope, okay, no, that's the proton, okay, from a hydrogen, okay. Carbon, okay, so carbon NMR, okay, so the most abundant carbon, okay, most abundant isotope kind of carbon 12, okay. So this one kind of about 99%, okay, so and then following kind of another carbon isotope kind of carbon 13, okay. So this one, just about kind of 1%, okay. So there are some other kind of the carbon isotope, carbon 14 something, okay. So that's just kind of almost very few kind of abundance, okay. Right, and then we know in the class, okay. So not all the atom, not all nucleus be NMR active, okay. So has to be either the nucleus or number or neutron number or kind of proton number, okay. Either neutron number or proton number are odd number, okay. So either of this, okay. So but for the carbon 12, okay. So both neutron number and proton number, okay. So both are 6, okay. So that's an even number, okay. So that's being said the carbon 12 kind of not NMR active, okay. For carbon 13, although they are the proton number is 6, but the neutron number is 7, okay. So that's the odd number, okay. So then that's carbon 13 will be NMR active, okay. So that's please keep in mind, okay. But because the carbon 13 kind of very last abundant, okay. So 100 carbon you only get one carbon, kind of about one carbon kind of carbon 13, okay. So that's why the carbon NMR signal kind of very weak, okay. So also the carbon NMR, okay, so we leave a kind of C13 NMR, okay, so that's because we only record kind of the C13 carbon, okay. And so carbon NMR signal kind of C13 carbon signal kind of 6,400 times less sensitive than kind of proton NMR, okay. One reason kind of very kind of last abundant for the carbon 13, another kind of the carbon 13 gamma value, okay, so that's it's also kind of pretty weak compared with kind of protons, okay. So because of such less sensitive, okay, so if you want to record carbon NMR, okay, so it's easy kind of just bury under kind of the other noisy signal, okay. So if you really want to get kind of decent carbon NMR signal, okay, so you have to kind of take many kind of scans, okay, and then build up kind of the signal, okay, and then cancel out kind of noisy, and then you can get kind of some decent kind of NMR, carbon NMR, okay. So normally speaking, kind of proton NMR, okay, so take 1 minute to get it, okay, but the carbon NMR, okay, so take maybe 5 to 10 minutes, okay. Reason for that kind of proton NMR, maybe 1 or 2 scans, you can get a very decent one, okay. Carbon NMR, okay, maybe 12, 14, 20 scans, you can kind of very nice carbon NMR, okay. So the reason for that kind of just say certain kind of less abundant, okay, and also kind of very small gamma value, okay. Right, but good thing about the carbon NMR, it has kind of the very sensitive to the environment, okay. So then it has kind of a larger scale, okay. So remember for the proton NMR, okay. So the scale is pretty much from the 0 ppm, okay. So to about kind of about 10 ppm, okay. And so the very small scale, okay. So if you have kind of many kind of the proton signals, okay, quite easy get overlapped, okay. So so that's the actual kind of for the real research, okay, I have this kind of situations, okay. So so multiple people get the same kind of the chemical shapes, okay. So but won't happen to the carbon NMR, okay. So for carbon NMR C13, okay, so because they are much large scale, okay, so from the 0 ppm, okay, until 220, okay. So that's the P easy to distinguish, okay. So in other words, okay, carbon NMR signal, okay, so normally you won't get overlapped signals, okay. All right, and then what kind of information can be provided by carbon NMR, okay? So first is okay, so number of proton, number of different proton, okay. So we call kind of distinct, number of different kind of carbons, okay. So right, so what kind of information can be provided by kind of carbon NMR first? Yeah. Number of different carbon, okay. So that's similar to the number of the proton signal, okay, in the proton NMR, okay. So yeah, right, okay. So the first thing, okay, and then that's we call it chemically distinct carbon, okay. And then second kind of the chemical shift of the carbon, okay. So this one is also similar to proton NMR, okay. So depending on what's the chemical environment of the carbon, okay. So it's shielding or de-shielding, okay. So then the carbon will have kind of different chemical shift, okay. So from 0 ppm and maybe until 220, okay. Right. And so yeah, we have the carbon NMR kind of chart, okay. So yeah, that's provided for you guys, okay. So you can see kind of different kind of chemical shift, okay. So you can use this chart for the future exam quiz, okay. Right, and then for the carbon NMR, normally we also add a little bit of TMS as the reference, okay. So as reference, okay. So so TMS kind of carbon, okay. So normally we won't see it, okay, but quite often, if we see kind of a small peak at kind of 0 ppm, okay, kpm, that's not from your sample, that's actually from the TMS, okay. Right, and also if you use CDCl3, okay, as a solvent, okay, and quite often you should see some kind of small peak about 77, okay. So 3, same intensity kind of peak, okay. So so this actually not from your sample, that's actually from the CDCl3, the NMR solvent, okay. So those 2 peaks, please keep in mind, okay. Right, and then for the carbon NMR, okay, so the different from the proton NMR, first they cannot provide kind of integration information, okay, because the intensity, okay, or the peak area, okay, of the carbon NMR signal, okay, not proportional to the number of carbon, okay, so no integration, okay. And second, okay, so carbon NMR, okay, won't split, okay, so there's no kind of the coupling, okay, so because we will run carbon NMR, okay, there are kind of technique called kind of broadband kind of decoupling, okay, so remove all the coupling, okay, so all the carbon, okay, you only think kind of singlet, no doublet, triplet, whatever, okay. So that's different from kind of a proton NMR, okay. Right, here's kind of real carbon NMR signals, okay. So for the isoacetate, okay, so you can see kind of for isoacetate, so totally 4 different carbons, okay, 4 different carbons, okay, and then that you see kind of 4 peaks, okay, all singlet, okay, no doublet, kind of triplet, whatever, okay. So because we should kind of decoupling, okay, so and also you see kind of small bunch of peaks here, okay. So 3 peaks actually kind of around the 77. Actually, that's from CDCl3, okay. So that's please keep in mind, okay. Sorry. Okay. So for carbon NMR signal, okay. So the purpose of the CDCl3 is kind of the first deuterium, okay. So you replace the hydrogen with the deuterium, okay, and then that's one showed kind of the solvent hydrogen kind of in proton NMR, okay, and then leave a little bit kind of the unchanged kind of proton in the solvent, okay. So reason for that kind of we can see kind of standard, okay. So internal standard instrument kind of will read this kind of area, okay. So if we find kind of 3 proton here, okay, so 3 signal here, okay, they will know the kind of this should be 77, okay, 77, okay, 77 kind of ppm, okay. So that's some kind of internal standard, okay. Right, okay. So that's kind of the next kind of just very general idea about kind of different carbon kind of the different chemical shift, okay. So for the CH3, CH2, and CH, okay. So those just the strong shielded, okay. So has a very low chemical shift about kind of 20 maybe to 40, okay. And if there are heteroatom, okay, like the halogens, okay, and also the nitrogen, oxygen attached carbon, okay, so then move to a little bit higher, okay, deshielded, okay, so about kind of 60, okay. And then alkyne proton, alkyne carbon, okay, very unique, okay, around 80, okay, so around 80, okay. Right, and then move to kind of 60 amount, okay, so region, okay. So for aromatic, the carbon and also alkene carbon, okay, so normally about kind of 120 to 140, okay. And then in the end, okay, comes kind of carbonyl kind of carbon, okay. Carbonyl carbon, okay, because carbon attach kind of the oxygen with kind of double bond, okay. Strong deshielding effect, okay. So those carbon has have a relative high chemical shift, okay. So about kind of 160 to 220, okay. But it really depends on what kind of carbonyl compound, okay. So lowest one is the aldehyde, okay. Lowest one kind of amide, okay, followed by kind of ester, followed by kind of carboxyl, okay. And then aldehyde ketone has relatively high chemical shape, okay. So for the carbonyl carbon, okay. So about kind of 200, okay. So for this kind of information, okay. So you still can use chart, carbon chart, okay. So that's fine, okay. But my suggestion kind of a little bit KPI idea, okay, KPI idea, okay. So what kind of carbon show in what area, okay. For example, okay, so I know kind of the CC amount of carbon should show around like kind of 140, 160 something, okay. So and then the carbonyl, okay, should be around like 200, okay. So that's a little bit idea, okay. That's will help you kind of solve exam quiz and question kind of quickly, okay. So all right, okay. And then second information, okay, so that's we talk about chemical shapes. Second information kind of the different number of carbons, okay. So that's very similar to protons, okay. So we know the kind of the equivalent kind of proton, equivalent kind of carbons here, okay. So if two carbon kind of relate to kind of mirror plane or kind of rotation axis, okay, then these two carbon will have kind of same chemical shape, okay. Right, example showed here, okay. So it's benzoic acid, okay. Benzoic acid has the 7 carbons, okay, some carbons, okay, but it only showed the 5 signals, okay. Why is that, okay? Because there's kind of symmetry plane, also rotation axis cut through this molecule, okay, and then 2 and 6 are kind of related to kind of rotation axis symmetry plane, okay, and also 3 and also 5, okay. So those 3, 5 show 1 signal, and then 2 and 6 show 1 signal, okay. So that's why overall, okay, so benzoic acid only show 5 signal, okay. So later one skill, you guys need to learn kind of if I give you one molecule, okay, so you can also quickly tell me how many different kind of carbon signal you should see for one molecule, okay. So that's the important thing. So just try to find the symmetry plane, rotating axis, okay. If there's no symmetry plane, rotating axis, okay, and then all carbon should show kind of different signals, okay. Right. So here kind of a little bit practice for you guys, okay. So there are kind of 5 molecule, okay, and then you guys need to tell me kind of how many signal, okay. So carbon NMR signal, okay, I should say for each individual one, okay. Right. Let's do this, okay. Just do it one by one, okay. How many carbon signal I should say for A, okay. So anyone can type your answer in the chat window, okay. How many carbon signal, okay. 3, okay, that's pretty good, okay. 3, okay. Should be 3, okay. So 1, because this molecule there's no symmetrical, okay. Symmetrical, okay. So and don't forget to know here the carbonyl carbon, 2 and then 3. Okay, good, okay. Right, okay. So how many carbon signal we should see for B, okay, this one, right? 4, okay. So anyone get more than 4? Should be 5, okay. So for this molecule also, there's no symmetrical case, no symmetry case. So let's see all 5 carbons should show kind of different chemical shape, okay. So 1, 2, 3, 4, 5. All right, okay. So now we move to C, okay. All right. So for C, how many signal we should say for it, okay. C has symmetrical, okay. All right. So someone already correct the answer. Okay, 3, okay. 3 is the right answer, okay, because there's symmetry plane cut through, okay. So also rotating axis, okay. So this is the same, okay. This 2 methyl, same thing. This 2 CH2 are same, and then 3 here. Okay, good, okay. Right, and then how many signal we should see for D, okay. Still type your answer in the chat window, okay. How many carbon signal we should see for D, okay. Okay, right answer should be 5, okay. So that's good, okay. So again, there's kind of symmetry plane cut through this molecule, okay. These 2 will be same, okay. These 2 will be same, okay. So that's 1, 2, 3, 3, 4, 4, and 5, okay. So should be totally 5 signals, okay. All right, okay. So now we move to last one, okay. How many signal we should see for the E, okay. Right, anyone can provide the answer in the chat window. All right, so okay. This time 7 should be right answer, okay. because of this double bond, okay, so the breakup symmetry for the whole molecule, okay, all the carbon will show different chemical shape, okay, all carbon will show different chemical shape, okay. So then that's 1, 2, 3, 4, 5, 6, 7. There's no symmetry plan, so no rotating axis for this molecule, okay. So that's 7 carbon. Okay. All right, pretty good, okay. So you guys learn how to do it, okay. In the end, okay, just one more example, okay. So about kind of the different carbon signals, okay. So all right, so that's actually kind of you count carbon NMR signal numbers, okay, can help you identify the isomers, okay. For example, this is the carbon NMR signal for the CH10, okay, could be one of these 3 isomers, okay. That's the dimethyl benzene, okay. So the question asks kind of which dimethyl benzene give this the carbon NMR, okay. So we have the also dimethyl benzene and then meta-dimethyl benzene and also the para-dimethyl benzene, okay. All right, and then so you can use your knowledge we just learned, okay. So predict kind of how many carbon NMR signal we should see for each, okay. So for because of time, the limitation, okay. So I just quickly go through, okay. For the first one, okay, so we should see kind of 4, okay. So these 2 mass will be same, okay. So that's kind of simply plan pass through here like this direction, go this direction, okay. That's 1, and then that's 2, 3, and 4, okay. So totally 4, okay. And then for second one, we only we should see kind of 5, okay, because there are these 2 methyl and simply plan now pass through like this. Okay. That's 1, 2, 3, 4, 5, okay. 5 signals, okay, for here, okay. And last one kind of the para-dimethyl benzene, okay. A lot of symmetry, okay. So these 2 methyl should same chemical shape, okay. And then these 2 carbon, okay, should see kind of same chemical shape, okay. And then all 4 other the benzene carbon, okay. So this one, this one, this one, this one, this one, okay. Show the kind of another one, okay. So because they're kind of simply plan, like this, okay. So totally 3, okay. So now you can see kind of the 4, 5, 3, okay. And then you can look at kind of the carbon NMR signal, okay. So here, okay, show the kind of only 4 signal, okay. So that means definitely kind of this first one gave this carbon NMR signal, okay. So that's how do you though some kind of question just quickly use just the number of your signal, okay, and predict kind of which one give kind of this signal, okay. Right, okay. So that's done the class today, okay. So any questions? All right.